Okay, well. Yeah. All right, so let's talk about black holes. How big do you think they are? Are they real big or are they real small? All right, if there's a black hole, say about 10 miles from the surface of the Earth, it would engulf us within seconds. We would all vanish. We would all disappear. Having said that, do you think they're really big or do you think they're extremely, extremely small?
Medium.
Okay, so yeah, you just to medium just in case. All right.
Big and small.
Okay, let's say when you say medium, do you mean are they bigger than the Earth or smaller than the Earth? That's what I'm interested in.
This one in particular, I think, is smaller than the Earth.
All right, here's the problem. If it's smaller than the Earth, how do you get sucked into it? It sounds like it's going to be a really constipating experience, right?
Yeah.
So you kind of like that to be smaller for one of the reasons. So if that's the case, how small is small? Do you think the size of the black hole is going to be the size of the United States, Chicago? The size of the building that you're in? The size of the room that you're in? We can make it smaller. Do you want to make it to be the size of a baseball, basketball, soccer ball, baseball? How about the size of a marble? How small do you want to go? We can make it small, about the size of a molecule. It could be the size of an atom, right? Or it could be even smaller than an atom. All right, so you can make it big. It could be much bigger than the Earth, or it could be as small as an atom, or it could be even smaller than an atom. So the black hole, the size of the black holes, how big do you think they are? All right, so that's what we're going to look into, that question. So what happens if you were to fall into a black hole? Where does the missing mass go? Now, you can look at it from two perspectives, right? It's just like the plumbing system. Right? Either you'll go to the center and clog it up, or you will go right through the center. If you were to go right through the center, where would you go? All right, you will go to the other side of a black hole, but what do you have on the other side of a black hole? So where did the missing mass go? Any ideas? All right, guys, just jump in if you have any ideas or thoughts or whatever that you want to share.
More mass is absorbed into the mass of the black hole.
All right, so Isabella, I'm going to give you 5 points. So that's one way of looking at it, right? More mass is going to fall in, and so which means that the more mass is going to get crunched up right at the center. That's one way of looking at it. All right, so it's going to act like a plumbing system in a sense that it's going to get clogged up. All right, so that's one way of looking at it. The other way, yeah, go ahead.
If you fall into one, don't you just kind of become spaghettified and all of your atoms just kind of get ripped apart?
And then what happens?
That's an
okay, so
question.
no, I mean, I get that. So eventually you will get squeezed and squeezed and squeezed, and eventually what happens is going to squeeze the energy out of you, right? Whatever that means. And then what happens? So where do you go? So it'll break into your atoms and the molecules, and then what? All right, so we'll investigate. So these are the questions that we're looking at. So the black hole theory, let's check to see how well this works. All right, so speaking of black hole, this is a visual for you. All right, so if there's a mass around, the mass is just going to vanish into it. It's going to disappear into it. So that's what the black holes do. And this guy is an apparent black hole expert. I think that's what he puts on his resume. All right, black hole theory is not a new theory. Most of you guys think that it is, but in reality, it's not. You can trace the theory all the way back to this guy's name is John Mitchell, 1783. He proposed the following based upon this formula. This is the formula that you guys have seen in Physics 1. G represents the acceleration due to gravity, which is going to be due to the mass of the planet or a star. It's going to be inversely proportional to the size, square of the size, the radius of the star or planet that you're looking at. He thought to himself that there may be stars out there which are just so incredibly massive, generating such strong gravitational forces that even a light may not be able to escape from these stars. So if you look at these stars, in the fact that no light is able to escape, they will look black to us. So you call them the frozen stars, the black stars. All right, so the year is 1783, and this is the formula that got things started. Move forward a few more years. The year is 1795. This time, the guy who was looking at the same formula was a different guy. His name is Laplace. You guys will recognize him from Calc 3. He's a French mathematician and a physicist. He's actually writing a book in Newtonian physics at the time, and when he comes to this formula, he notices that the formula makes an interesting prediction. The prediction that the formula makes is the following. All right, let me just get this up. He notices that if you make the radius smaller, what's going to happen to the gravitational pull? It's going to get larger and larger. All right, so if you just take the Earth, for example, and squeeze the mass, make it smaller and smaller, what's going to happen is the gravitational pull is going to get larger and larger and larger. That's what he came up with. All right, so he's writing a book on Newtonian physics. He comes to this, he makes this discovery. I mean, he knew that the formula was correct because it would give you the correct gravitational acceleration, which is 9.8 meters per second squared. But what if you squeeze the radius, make it smaller, about a mile? what happens to the gravitational pull? It jumps up to 155 million meters per second squared, which means that now you're feeling 15 million times heavier. What would happen if you were to squeeze it further, make the radius about a meter? Now the gravitational pull jumps up again. This time it's going to be 400 million meters per second squared. Now you're feeling 40 million times heavier. Keep shrinking it. Make the radius about the size of an atom. So the gravitational pull becomes so large that the acceleration is going to be 4 trillion times trillion times trillion meters per second squared. Now the gravitational pull becomes so large that the mass is going to start to collapse in on itself. So the radius is going to tend towards 0. It's not going to be 0. It's going to tend towards 0. So as the radius starts to shrink towards 0, the gravitational pull is going to start to approach infinity. You created yourself a black hole.
You can be forgiven for thinking a black hole is some sort of weird science trick. An infinitely small, invisible star defies common sense. It's what happens when you use mathematics as your lens on the universe.
All right, so the black holes will be smaller than the smallest atoms in your body. So that's the size of a black hole. That's what the size of a black hole is. So the best answer is, based on the discussion that we're having, just jumping at this moment,
D.
it's going to be D. D as in David. Those of you guys who say D, give yourself 5 points. And
So
those of you guys who pick D, give yourself 2 points. Go ahead.
does light have mass?
Ian, I'm not going to answer that question, and there's a reason for it. I'm sworn to secrecy on that one, because we will have that discussion. Why did you even ask that question?
Well, if the
Oh,
strength
I
of
see.
gravity,
Okay, damn. Gravity acts on mass, right? So what does it mean? That implies that the light has mass, right? All right, beautiful connection. I'm going to give you 10 points for that one. I see where the question is coming from. We will have that discussion again during the next hour, so I didn't want to jump into it, but that's certainly the implication of this discussion. Anyway, so year is 1795, and Laplace is writing a book on Newtonian physics. And out of the blue, he says, wait a minute, there must be stars out there which are just so incredibly massive, collapsed stars, and they must be generating such strong gravitational forces. And the gravitational pull is so strong that the light is not able to escape from these stars. That's it. That's it. Except his friends, understandably, were alarmed. Guys, you're dealing with things which are smaller than the smallest atom in your body, generating these nearly infinitely large gravitational forces. It's science fictional. All right, when you have an idea like this in your head, instead of pondering about it, today you take medication for it. Because this sort of idea, you don't obsess over it, because this is the sort of stuff that would drive you nuts. And you certainly don't write it down in a book, because people will read it and think that you're nuts, basically. You don't want to advertise it. It's okay to be nuts, just don't advertise it. So his friend said, hey, listen, pal, we understand exactly what you're saying. That sort of argument comes out of mathematics, and that sort of mathematics does not have any basis in reality. Don't write it down in the book, all right? I mean, we understand that you're a genius, and just don't ruin it. So first publication had the prediction in it, so it's the second publication. Eventually, the guy, being a genius that he was, he came to his senses, and then that prediction vanished, completely vanished. Move forward to 1916, and this guy who looks like a comedian, who's not, his name is Karl Schwarzschild, happens to be an expert in the sort of mathematics that Einstein was using in developing his own theory of gravity, which is known as general relativity. Einstein publishes it in 1915, 1916. And those of you guys who don't know, this is the middle of World War I, and Karl Schwarzschild is in the military, German military. This guy is a mathematician, he's a physicist, he's a theoretical physicist. And he's in charge of trajectory computations for artillery, and life is boring, needless to say. So he gets all of Einstein's papers and he starts messing around with it, only to realize that Einstein's theory also makes the same sort of predictions about these collapsed stars, generating these nearly infinitely large gravitational forces. He gets all excited, writes a letter to Einstein, including his proof. Einstein gets the letter, marvels at Karl Schwarzschild's work. And then here's what happens.
World War I had just broken out when Albert Einstein publishes his general theory of relativity. Among those fighting on the Russian front is a German astronomer and physicist named Karl Schwarzschild. With a war raging around him, Schwarzschild discovers that Einstein's equations predict the existence of a star so unimaginably dense that even light cannot escape it. From the battlefield, he sends Einstein his calculations. Just weeks after receiving Einstein's reply, Schwarzschild dies on the front lines. Einstein marvels at Schwarzschild's work, but he never accepts that such a star could really exist. As he puts it, it just doesn't smell right.
So unlike Laplace, Einstein was a true genius. He looks at it, he says, oh, that prediction is coming right out of the math. And this sort of mathematics does not have any correspondence to reality. He ignores it completely. If it didn't fit into Einstein's common sense, as far as he was concerned, that was not reality, that was just mathematics. Lesser physicists than Einstein decided to take up the challenge. One guy in particular, Indian theoretical physicist Chandrasekhar. He's a guy who actually kept working on it until there were some observable predictions. And that is what happened. The first black hole was discovered in 1970s, for which he won the Nobel Prize in 1983. Go figure. Evidently, regardless of your common sense, if there's a mathematical prediction, we take it seriously today. Physics is completely different. A lot of what we deal with are counterintuitive in modern physics. It does not fit into any sort of imagination or understanding that we have. Everything is extremely mathematical, a lot of which cannot be visualized. And then it appears that the nature is mathematical. All right, so this guy ends up winning the Nobel Prize for something that Einstein decided to reject.
60-second adventures in astronomy, number 12, black holes. DIY tip 34, how do you make yourself a black hole? A black hole occurs when something has so much mass in such a small space that nothing can escape its gravitational pull, not even light. In 1931, Subramanian Chandrasekhar calculated that if a star is big enough, when its fuel runs out, there is nothing to stop gravity from making its core collapse to create a black hole. Unfortunately for Chandrasekhar, his contemporaries, like Sir Arthur Eddington, just didn't believe him, but it turns out he was right, and in 1983 he eventually won a Nobel Prize for it. So if a star is big enough to begin with, when it collapses it becomes so dense that its gravitational pull won't let objects or light escape. In fact, you'd make a black hole if you crushed any object until it was small and dense enough. But you don't always have to crush something to make a black hole. The bigger one is, the less dense it needs to be. So you could make one out of tap water, but the required amount will fill the space between the Sun and Jupiter, and sadly there's not enough water in the galaxy for that. So for you DIY enthusiasts, you'll probably have to order it in specially.
Chandrasekhar, the winner of the 1983 Nobel Prize.
We had this meeting at the Institute of Space Physics in New York. I said before we reach a final conclusion, we ought to throw into the pot still another object, a gravitationally completely collapsed object. Well, after you've used the phrase, a gravitationally completely collapsed object, 10 times, you conclude you've got to get a better name. So that's when I switched to the word black hole.
The word black hole, which John Wheeler coined, suddenly caught on. Everybody adopted it. And from then on, people around the world, in Moscow, in America, in England and elsewhere, could know they were speaking about the same thing. And not only that, but it suddenly, the whole range of concepts got through to the general public. And even science fiction writers all of a sudden could talk about it.
All right, so what was the original name of the black hole up until 1967? It was...
Gravitational fully collapsed object?
Okay, damn. It's gravitationally completely collapsed objects, right? All right, so I'll give you 5 points for it. I almost couldn't remember it. Anyway, so it's gravitational completely collapsed object was the original name until John Wheeler came along in 1967. He decided to coin the term black holes. All right, so the term black hole kind of captures your imagination, doesn't it? In just about every single language, the term being used is black hole, with the exception of French. I don't know why. I think it loosely translates into a dying star collapses into an asshole or something, so the French are kind of sensitive about it. And John Wheeler was kind of offended by that interpretation, so he said black holes have no hair, whatever that means. I think the only French probably would get that meaning. But in every single language, it's black hole is the term that we use. John Wheeler is an interesting character. One of the biggest names in physics who did not win the Nobel Prize. All right, one of the most influential physicists in the United States who did not get a chance to win the Nobel Prize. Two of his students did. One of them is Richard Feynman, my hero, considered to be the best theoretical physicist of the 20th century next to Einstein. And the other guy is Kip Thorne. All right, Kip Thorne is the guy behind the movie Interstellar as well as Contact, who won the Nobel Prize for LIGO recently. All right, so this guy is a big deal, John Wheeler, 1967, the guy who coined the term black hole. Of course, the black hole theory became fairly famous because of two guys. One of them is, you're looking at it, it's Stephen Hawking. This was part of his PhD dissertation in the 1960s. And then obviously started publishing books in the 1980s for general public, captured the public imagination. Obviously a lot of the science fiction about time travel and parallel universes are kind of loosely based on his books. The second guy who's just as big as Hawking is, this is Penrose, Richard Penrose that you're looking at. All right, he's also has published quite a few books, except his books are by and large mathematical. So though they're accessible to public, you need to be a physicist or a mathematician to be able to actually decipher the books.